working, it came here and it made the other, okay. Let me try to write it here. Let me try to, I don't know, maybe do this. Okay. That's very, this is nerede oluyor? Doğru gören var mı? Okay, good. I guess I can do this way. Okay, process 0 and process 1. Okay, when process 0 starts running, okay, okay, the other is in this case for the process 0, what? 1. And this is our array, interested array. Okay, interested array. And what else? We have the turn, right? So for this one, other is 1. And interested process true. So I put the T there, right? And turn is process, and I make it 0. Okay. Initially, turn is 0, and the values of these are false and false. Okay. So I come here to the turn gets the value of process, and I run this loop. Turn, if turn is process, okay, turn is the process number, okay, this is my process, 0. This is true. And interested other is true. Is this correct? Does this hold? Interested other true? No. So this while loop immediately breaks, and it leaves the function. So I can enter my critical region. Okay. So when I am done with the critical region, what I do is I make my interested process false. So I make this true, false. So both of them are false. When process number 1 starts working, it does the other way. So it works. Let's look at the race conditions. Let's look at the worst thing that can happen. Okay, what is the worst thing that can happen? When you do the switch between process 0 to 1 at the worst place, where is the worst place that it would happen? Both of them would call this enter region. Okay, at the same time. They are running at the same time. Okay. So continue. Where is the? Both of them are running it. Process 0 started. Okay. It came here, and other is 1. This one is other is 0. Okay. So interested process true. Okay. One of them. Okay. So process number 0 makes this true. Okay. Process 0 makes this true, and it takes the turn as 0. Okay. So I come here for process 0. Then at this point, context switch happened. And I switched to process number 1. Process number 1 came into the picture, and its other is 0. Okay, and interested process true, and it made this true, and it made the turn 1. Right? It made the turn 1, and then it came here. It says that turn is the process. Okay, this is correct. And interested other true. What happened? would this while continue or would this while break? It continues, right? Because turn is 1. Okay, we are talking about process number 1. Turn is 1. Okay, turn is 1. And the other interested other is true. Both of them are true. So this while loop has to continue because there is a semicolon there, right? So this while loop has to continue for process 1. So process 1 enters in a busy loop. Okay? Process 1 enters in a busy loop. This will continue. The busy loop will continue until when? Until infinity? No. The busy loop will continue until there is an interrupt occurs, right? There is a timer occurs because you use so much CPU time. The operating system takes the control from process 1 and the control goes to the process number 0. Let's go back to process number 0. What does the process number 0 do? It comes here that says that, okay, see it was here, turn, it made this, it thinks that it made this assignment of turn, it gets the value of 0, and it thinks that the value of the turn is 0. It comes here, and it looks at it. If turn is 0, but the turn is not 0 anymore because turn made by the other process as 1. So this loop breaks and process number 0 quits from this, returns from this function, and it goes into the critical region. When it is done, it comes back and it says that interested process, interested 0, false. So it makes this false. Okay, it makes this false. And then when it is time for the other process to continue, it comes back with this loop. It says that, okay, turn is 1 and interested 0 is not true anymore, it is false. Then the process number 1 can continue its work. Okay? So even the context switch happens at the worst place, even the control switch happens between 0 to 1 or 1 to 0. At the worst place, this works. It doesn't get into the problems of race conditions. Okay? This is called Peterson's algorithm. 1965 or whatever. We don't care when it is invented, but that's the solution. So what is the main idea of the solution actually? Can you see the main idea? Well, one of them is this, yeah, I mean the answer is you do this, okay, you make this assignment and you check if the assignment is hold, but if you do that assignment, okay, without this part, this goes into an infinite loop, right? So it is not only that. The other thing is that you check the array of the other one. Okay, race conditions happens this way. It always happens this way. You read something to your register, okay? Context switch happens. Whatever you read and the memory changes, it is different. When you try to write to the same memory location, you write the wrong thing. So the problem is reading and writing, right? When you write it, you mess it up. In this case, you are always writing to some other place, okay? Everybody is writing to their own array position. There is an array position for each process, and you are writing to that array position. Since each process is writing their own array position, they cannot interfere with each other's positions. Okay? So that's a very clever solution. If the other process is not interested, you immediately go into the. If the other process is not interested, you immediately go into the critical region. If the other process is interested, and you are trying to do the same thing to you go into this infinite loop, because turn can be either 0 or 1. Okay, this one can only be 0 or 1. So either of the processes will break this rule. I mean, this loop cannot continue for both of the processes at the same time. One of them has to break it. Not two of them can break it at the same time because they are running this, right? They are running this. Okay, any questions? Anladık mı multi-testing algoritmasını? Adam akıllı, bunun bir daha karmaşık sonuçlar varmış. Sadece bir yere yazıyor adam. Yani herkes şu array'in kendi yerine yazıyor. Turn'le beraber bunu kontrol ettiğiniz zaman da çift mekanizma falan gibi. İkisi birden critical region'a giremiyorlar. Çıktıkları zaman hemen kendi yerine ben artık ilgilenmiyorum diyor. There is no strict alternation for this one, right? Same process can enter the critical region many times and can leave it without waiting for the other process. So there is no problem with the strict alternation. What was the problem with the strict alternation? You have to wait for the other process to critical is non-critical region. Okay. This one process 0 can enter the critical region many times without waiting for the other process. Okay. Bir tane soru sorun çabuk olun. Zamanım yok, bugün ara vermeyeceğim. 12.30'da bir toplantım var. Keşke söylemeseydim onu, şimdi erken bırakacak nasıl olsa. Geç kalacağım toplantıya, tamam mı?
Hocam bir şey sorabilir miyim?
Tabii ki.
Şimdi mesela 2 tane prosesimiz var diyelim. Birinci proses turn'ü set etti prosese.
Turn'ü 0 yaptı, evet.
Aynı anda ikinci proseste
geldi.
1 yaptı.
Evet. Birisi turn'ü tam biraz önce söylediğimi söylüyorsun. Geldi. Turn'ü 0 yaptı. Buraya geldiği anda diğer proses çalışmaya başladı. Değil mi? Turn'ü 0 yaptı. 1 yaptı da. Değil mi? Buraya geldikleri zaman 0. proses geliyor buraya diyor ki 0. proses geliyor buraya diyor ki turn proses number'a, kendi proses number'a bakıyor. Turn diyor 0 mı? Turn 0 değil. Değil mi? Turn 0 değil. Turn 0 değilse o zaman çat diye hemen buradan çıkıyor. Ama öbürü oraya geliyor. Kendisi turn'ü 1 yapmıştı ikincisi.
Evet.
Turn 1 ve diğeri de zaten interested. Adam interested demişti kendisi. Dolayısıyla orada beklemek zorunda kalıyor. Yani ben turn'ümü 1 yaptım ama diğeri de interested olmuş. Anladınız değil mi? Buraya geldi. Her ikisi de kendi interestlerinde turu yaptılar. Buraya geldi. Burası bakın her biri için ayrı yer. Burası ortak yer. Her biri kendisini turu yaptı. Buraya geldiler. Sadece bir tanesi buradan geçerken turn ya 0 olacak ya 1, ikisi birden olamaz değil mi? Dolayısıyla şu interested true ikisi içinden doğru olabilir ama sadece bir tanesi için turn eşit proses olabilecek. Tamam mı? Olmayan dışarı çıkıyor. Öbürü beklemek zorunda kalıyor. Neyi beklemek zorunda kalıyor? Diğerinin işini bitirip interested prosesi false yapması. Interested prosesi false yaptığı zaman diğerinin turn'ü kendisiyle aynı olmasa bile oraya giremiyor. Tamam, bunu birazcık düşünün siz. Sorun mu? Tamam, sorun madem konuşuyoruz.
Hocam, turn'ü volatile yapsaydı bir tek kendisi değiştirecekti, diğeri de etkilemeyecekti ya, o sıkıntıyı...
Turn'ü volatile yapsaydı?
Yani global değil de volatile yapsaydı sadece...
Volatile yapınca ne oluyor ki? Volatile demek her zaman bir şeyi okurken register'dan okur, register'dan durduğunu düşünme demek. Register'dan gidip okuyorsun. Yani volatile yapmak bunu atomik yapmıyor. Volatile demek bir değişkeni register alıp register'ın üzerine işini yapma. Değişkeni eğer okuyacaksan sürekli olarak register'dan oku, öyle yap demek. Ama register'dan okuduktan sonra context switch olabilir. Volatile yapmak hiç çözmüyor yani. Atomik yapmıyor işte. Yani belki birisi okuyorsa, birisi ona yazıyor, sen okuyorsan olabilir belki. Ama sen hem okuyor hem yazıyorsan volatile yapmanın bir manası yok. Evet.
Instead of doing this kind of software tricks, why don't we make an special register in CPU so when
But you can get the hardware help. That's the next topic actually. We will talk about it. So instead of developing this kind of, the suggestion instead of developing this kind of software-based solutions, let's use some other type of. Let's say, if I can do with the, remember this one. If I can do these two things atomically, that means that if hardware gives me a guarantee that there cannot be any context switches or interruptions while you are doing this, then you should be all fine, right? So that's the suggestion, and that's what we are gonna look at next. Okay, TSL, test and set instructions. Okay, this is a special kind of instruction, TSL. Okay. TSL instruction, this one. What it does is, okay, it copies the lock variable, okay, lock variable to the register, okay, it copies the lock variable to the register and sets lock to 1. Test and set lock, okay, TSL, test and set lock, and it's a single instruction. So it is done atomically. That means that while you are executing this instruction, no interruptions can occur. Okay. So it does two things. It copies the value of lock variable to the register and sets lock to 1. Okay, sets lock to 1. Then after immediately doing this, you compare the register value. You compare the register value to 0. Okay. If it is 0, then that means that if it is 0, then that means that lock is available. I can go into the critical region. If the register is not 0, that means that somebody else locked it. So I go into this loop. It's exactly the same as the lock variable solution, but this time we use a special instruction provided by the CPU, not the operating system. It's an instruction assembly language. This one is okay. So this special instruction does two things at the same time without getting interrupted. It copies the lock value to the register and sets the lock to 1. And you compare the register with 0. Then if the register is, what does it mean if the register is 0? This means that nobody has locked it. If the register is 1, that means that somebody else locked it, so I need to go into that loop. Otherwise, I can get into the critical region. And when I am leaving my critical region, I just do this. What does this do? Move lock 0. Okay, store 0 is locked. That means that, okay, this lock is now available. Anybody who wants to lock it can lock it. Okay. So this is not a special instruction. This is a regular move. Okay. Then we have only one special instruction. It is this one: test and set lock. Okay, and it is done atomically. If there is a context switch happens, okay, if there is a context switch happens, when right here, okay, if a control switch happens right here between process A and B. Let's say process A is running and it runs this instruction. So it copied the lock value of 0 to register and it made the lock 1. Okay, now the lock is 1 and the register value is 0. Then the context switch happens. B is trying to do the same thing. When B tries to execute this instruction, says that, okay, copy the lock variable to register and set lock to 1. So for process A, the register would contain 0. For process B, in this case, register would contain 1. Okay. So when process B continues, it sees that register is not 0, so it goes into this loop. But for A, since register is 0, it will leave this part with the return, and it will go into the critical section. Okay. So this is how we get help from the hardware. Any questions? Yes.
Hocam bu durumda birbirleriyle alakalı olmayan iki programda birbirini locklayamaz mı? Lock ortak kullanılıyor programları.
If those two threads or two processes have nothing to do with each other, then they should not lock the same variable, right? Lock is a memory location. Okay, lock is a memory location. If those two processes have nothing to do with each other, then they should not use the same memory location. That's a programming error or design error. Okay.
Operating system halinde yani. memory location operating
In order to share a memory location, at the beginning of the program, you need to declare that these two processes are going to share the same memory location. Or these two threads, since they are in the same user space, okay, they are sharing the same memory location. I mean, the thread in the same user space, threads are written by the same programmer. So, if the programmer knows what he is doing, then there should not be a problem. You cannot by accident, I mean, if you are using somebody else's position by accident, that's the same problem as using the dangling reference, dangling pointers. I mean, you need to be careful. If you design your system right, no problem. There is no lock variable. There are as many memory locations as there are as many lock variables as the memory locations. Okay, any other questions? Then continue. This TSL is not a standard CPU instruction. For other systems, like some Intel Core systems, there is another CPU instruction called exchange. Okay, exchange. What exchange does is that it exchanges the values of register and the lock variable. Okay, so if register is 0 and lock is 1, it just switches them. Okay, exchanges. Swap the contents of the register and lock variable, and it does this automatically. So first we make the register 1, and we try to exchange it with the register. Okay, with the lock and the register, and compare the value of register with 0. If it is 0, then that means that okay, I already locked it and it wasn't locked before.